Well, hello and welcome to this episode of the Global Classroom for Exploring the Stars Part 2. Now, I am delighted to welcome Dr. Stefanie Milam back in the classroom today and to share with you some exciting updates on the extraordinary James Webb Telescope. Now, Stefanie is a planetary scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and serves as the James Webb Space Telescope's Deputy Project Scientist for Planetary Science. Quite a tremendous achievement. And first of all, make sure we can see you. First of all, Stefanie, hello, how are you?
Hi, I'm doing great. Thanks again for having me back. This is a really exciting day.
Now, last time we spoke to you, we'd got through that incredibly complicated part of the telescope being deployed. It was like fingers crossed, toes crossed, everything crossed time as it unfolded in space, and you were just starting to receive some of the images that were coming through the James Webb Telescope, and you shared those so kindly with us, and we were all very, very excited about it. And what I can say is that all across the world, you know, the reaction was tremendous, and young people were inspired to see what we were seeing beyond our own imagination in some ways, and the clarity and the depth of that was just phenomenal. And your explanation was brilliant of understanding how this is not just a project that you're working on. This is a global project, a time when we're all coming together in positivity to create something extraordinary and to learn new things as well. And so what actually have you been doing since we last spoke to you and now anyway?
Well, we have actually been doing science. We are now using the telescope in all the ways that we had hoped to. We're observing objects, distant objects in the far universe. We're watching supernova. We're studying the solar system. We're looking at planets around other stars. We are doing all the science that we had intended to do. It's pouring in. We're getting new images daily. Everything is state of the art. It's better than we were expecting. And people are working very diligently to try to publish their science results in a timely way. And in the meantime, we're trying to feed the community, the public, little hints of what's to come as far as the science. So releasing images here and there. And I'll get to talk to you about our latest one that we just released yesterday, actually.
Right, so before we get going, first of all, I must forget to say a huge thank you to San Christian School in Spain, who wrote in last time about this event, and they said, please mention our school before you start the Global Classroom. So hello to them as well. And thank you for all the questions sent in from around the world. And I'm going to invite Stefanie in a second to share with us a presentation about what's been happening and going on with the telescope and the images as well. Before we do, this session is slightly different than last time. We're going to have some questions coming in from around the world have already been sent in, and then halfway through our episode, once Stefanie's finished talking, we're going to invite you all to take part, no matter where you are in the world, whatever you're doing. If you're in a classroom with your teacher, is to add things into it, because via Teams you have now got the Q&A system open, also via social media. You can find all those links there at, I'll get this correct now, theglobalclassroom.com, and we are opening those feeds now for you. But also in Teams, the Q&A tab at the top, you can post a question at some point throughout the presentation, and once we've answered the questions that have already been sent in, we might raise yours to Stefanie as well, have a discussion about it, and put it in there. If you can do, add your name onto it so we know it's from you. Otherwise, it could be a random question coming in. So if you've got that, we're all set. If you are looking for a stream in a different language or translation, please turn the captions on the top right, about here on your screen. But before we go any further, this session is really about Stefanie talking to you about the amazing pictures and findings from the James Webb Telescope. So Stefanie, over to you.
Thanks so much. Let's make sure I get my sound turned on. And presenting. Okay. So again, I'm so happy to be back and to get to talk to you about all of the things that we've been doing since I last got to speak with you. We have been working really, really hard on making the telescope be a fine-tuned machine, operating in very systematic way, collecting images and spectra of everything across the universe, the same way previous observatories have done, including the Hubble telescope and others. So I'm going to share with you a little bit of this journey that we've been going through since we last spoke.
De compte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
Hard to believe it's been
And we have engine start.
9 months since we had this day.
And liftoff.
Décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
It was a really exciting day for all of us.
Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
And it was just the beginning.
And let's go down to the floor in the Jupiter Control Center.
We sent our observatory 1 million miles away from Earth. We passed the moon and we got to what's known as a second Lagrange point within about a month after launch. This was a long journey for us. That first month was extremely intimidating, as I told you last time. While we were on that journey, we were unfolding our telescope, watching with a very keen eye to make sure everything was unfolding and deploying properly in space. And then we went through a whole series of testing the instrumentation, making sure that the mirror was focused properly. All of our science instruments, the heart of the telescope, actually was working the way that we really wanted it to. And we really wanted to understand how to control the observatory and get the scientists prepared for what was to come. But we still had no idea what was really underway. So just a quick background, in case you missed the last episode, we are known as the successor to the Hubble Space Telescope, but we're extremely large. So the James Webb Space Telescope actually has a 6.5 meter diameter primary mirror compared to what the Hubble Space Telescope has. It's only about 2.4 meters. So it's a huge mirror. You notice that it's extremely different in shape, in color. Everything about it looks completely different than what we've known standard space telescopes to look like. If we have a standard, I guess Hubble is what most people would associate that as. We operate at infrared wavelengths, so we actually see into the infrared light or the thermal light. It's like having night vision goggles, so we can actually see into space in ways that the Hubble Space Telescope could not see. So these are longer wavelengths, infrared, which is we are optimized to do because we can see different fingerprints of molecules that we're really interested in studying in stars around our planets around other stars. It also allows us to see the very first stars and galaxies that were formed in the universe, because that light, just as our own sun emits at visible wavelengths, that light of those first stars actually gets stretched to longer and longer wavelengths. So by going into the infrared, we actually have access and now the goggles, the night vision goggles, to see those very first stars and galaxies. But because this telescope's so huge, we actually had to fold it all the way up. You can see me here standing in front of it. It stands about 3 stories tall. It's absolutely an amazing feat of engineering and a very impressive observatory. This is where I left you last time. I was showing you our first images that we were getting as we were testing our instruments. This shows you all of our science instruments, and including our fine guiding sensor, looking at a beautiful star field. The resolution that we were able to see is just absolutely impeccable and blowing our minds. So this is comparing one of our other predecessor telescopes, the Spitzer Space Telescope, compared to the James Webb Space Telescope, but almost the same wavelength. And you can just see the clarity and beauty that comes through these images. So we already knew at this moment in time that things were going to be great, but we had no idea how great they were going to be. So I'm going to walk you through all the excitement that we've actually been going through since we released our first images, which was in July, and give you a little bit more insight into some of the other things that have come out since then and what we're working on. So this was the first deep field image, but this is not the James Webb version. This is actually the Hubble Space Telescope version of the SMACS 0723 deep field. What you can see is a whole series of galaxies. There's 5 yellow dots sort of scattered across the center of this image. And those are massive galaxies that actually are creating a lensing effect. So they're pulling light from around them, which is why we see these funny little smeary, streaky things going around the outside. So if we go from the Hubble version to the James Webb version, you can see all kinds of things start appearing. We see a lot more red and blue dots scattered around the background of this image. The clarity is just impeccable. You can zoom in and zoom in and zoom in on this image, and you're always going to find something new. It's amazing the amount of clarity that you can see. You can see spiral galaxies in the background, halo galaxies, and even more of these sort of streaked and smeared lensed galaxies from the background. This image blew our mind. It is a tiny speck of sand if you were to hold it out on your fingertip. That's the size of the sky that we're actually looking at with this image. It is a tiny little fraction of the sky, and we're seeing thousands of galaxies already with only 8 hours of James Webb Space Telescope time. We've been observing for 2.5 months now, and you can imagine how much science we've already revealed, considering this is only 8 hours worth of time. So we're moving into a whole new era of extragalactic, deep universe studies and revealing things that we've never been able to see or study before. Another really cool image is one of our planetary nebula images known as the Southern Ring Nebula. So again, this is the Hubble Space Telescope version image of this object. Planetary nebula is sort of a misnomer. Has nothing really to do with planets. These are stars that are dying. As a star dies, it loses all of the material, the matter, the energy that was contained within that star, and it blows it away. And what you're seeing is shells of gas and dust that have been actually ejected from that star, creating sort of a cocoon of dying material around the dead star in the center. When I was a student, I remember seeing these Hubble Space Telescope images and thinking, wow, this is just one of the most beautiful objects I've ever been able to see. Nothing is going to ever surpass what the Hubble Space Telescope did. Well, little did I know, with the James Webb Space Telescope, it's just blown it away. The clarity, again, that comes out, you can now see not only those shrouds of gas and dust, but you can see how they've been actually ejected, and you can see light penetrating through them and streaking and escaping through that cloud. You can see background galaxies in this image that we didn't even know existed. There's this beautiful photobombing galaxy, Edge-on galaxy, sort of right on the left-hand side of the image, which is just absolutely astonishing that we're seeing these types of things just everywhere. We see galaxies everywhere. They are now a contaminant almost in every image that we look at. And when we look at this image at even longer wavelengths with the James Webb Space Telescope, even new things pop out beyond what we were able to see in the near infrared. So now in the center, you see not only one star, but 2 stars. There's a red one and a blue one. So this is actually a binary star. The red one on the left is the one that's actually dying, that's losing all of the material. The binary star is actually a really young, bright star, and what it's doing is irradiating or illuminating all of that gas and dust and making it glow in ways that are absolutely beautiful. The color reflects the different molecules or dust that we're seeing in that cloud of material that's being lost from the star, and it helps us understand what process happened, how that star died, and how it's going to evolve even beyond this phase of its evolution. So this is really exciting science that's coming out, and we're looking at new planetary nebula all the time. If you follow on social media, there's a lot of bots now that are following what James Webb Space Telescope is actually observing in real time. And you'll see planetary nebula pop up at least once or twice a week. So it's really exciting to know and that these kinds of objects are being studied routinely, and what we're learning and the science that's going to be revealed in the near future is only the best of what you can even imagine. My favorite image is Stefan's quintet. So this is 5 galaxies. Sometimes that's hard to see. So in the Hubble Space Telescope image that you're seeing here, there's 1, 2, 3 that are merging kind of in the middle on the right. one down on below. So that whole series of 4 galaxies are actually extremely far away. The one on the left-hand side, this more sparkly, twinkly galaxy, is actually a lot closer to us. It just happens to be in the direction of the sky of the other 4 galaxies. So it's kind of the giant photobomber of this particular image. So let's move to the James Webb Space Telescope version. And you can see, again, all the glitter that pops up in the background of this image. These are all galaxies that are being revealed for the first time and things that we haven't been able to study in this kind of detail. Because of the wavelengths the James Webb Space Telescope operates in, we are seeing further now behind this whole series of galaxies, and all of those distant objects are starting to be illuminated through the eyes of the James Webb Space Telescope. This galaxy has, or this image has a lot of really cool features being demonstrated, and only just the skim of the surface of the science to come. The top image, or the top galaxy in this image, is actually what we call an active galactic nuclei. So this is a supermassive black hole in the center of this galaxy. And what you're seeing is a swirling of dust and gas that's actually being sucked into that black hole. There's also, in this collision down here of the 2 galaxies in the middle on the right, you're seeing where a lot of stars and other objects are being formed and sort of energized through the merger of these 2 galaxies. The one on the left, the beautiful, glittery, sparkly, photobombing galaxy, again, we're seeing a lot of stars and new planets that are being formed in this sort of red, dusty-like material that's scattered across that galaxy. When we go to longer wavelengths, you're seeing even more clarity. The active galactic nuclei on the top is now almost revealed. We can't image black holes directly, but what we are seeing with the James Webb Space Telescope is all the dynamics that are happening around a black hole. The types of influence it's having on its environment, sucking in material, sort of eating away this galaxy, but also how it's sort of stirring and mixing all of the material of the galaxy, all the stars, all the planets, all these giant clouds of gas and dust, how they're now being sort of mixed together and colliding with each other, and how that's causing a lot of energy and a lot of radiation to be emitted. You can now see the 2 merging galaxies a lot more clearly in this image. And again, the photobombing galaxy on the left is absolutely spectacular. This is one of my favorite images of, or one of my favorite versions of this image, because at these wavelengths, it really looks like a series of jewels scattered across the sky. I think it's absolutely beautiful. And of course, my favorite image that we released with our early release observations was the Carina Nebula. So I have the Hubble Space Telescope version of this. And what I want you to think about and consider when you look at this image, again, this is a very, very small piece of the sky. The Carina Nebula itself, you can actually go in and look up the full extended version of this image from the Hubble Space Telescope, and it's huge. And you can just zoom in and zoom in and zoom in. And this, what we have imaged here, is just one tiny little fraction of this entire star forming cloud. This is a cloud in the universe, the same we have clouds in our sky, that is actually obscuring gas, or it's gas and dust that's obscuring light from behind it. So it's like a curtain almost that you can't see through with your own eyes, just the same way we can't see through clouds in our own sky. But when we go to longer wavelengths with the James Webb Space Telescope, we put on our night vision goggles and we can see right through it. You see this whole field of glitter in what looks like giant mountains. This is the cloud of gas and dust that we can now see inside of. We can see baby stars. We can see planets starting to form. And then on the top, what looks almost like a starry night, the darker half of the image is where stars have actually already formed and already eaten away that cloud of gas and material. That's what stars are actually being born out of. And so as they start forming, they eat away all of this gas and dust. So they eat this giant mountain. and they form new stars. And so what we're seeing within the mountain are the baby infant stars starting to collect all of that gas and dust. And then on the top are the ones that have already formed. There's a crazy interplay that we don't really understand on the stars that have recently formed because they're so bright and so energetic. They also will destroy material around them. But we also know that stars are already forming within that material. So what's that balance? How does that compete? Are we destroying more material than is actually there to form new stars? How do massive stars form compared to smaller stars? How does all this entire environment influence what kind of planets are formed around them? These are things that we have no idea about, and we're just starting to scrape the surface of. Planets around other stars are something that's extremely interesting. And one of the ways we want to study these planets is by doing something called transit spectroscopy. So what we're doing is, as a planet passes in front of its star, we see how that light is actually blocked. So just think about putting sunglasses on or watching, a lunar eclipse or a solar eclipse even. You can see how the light of the sun is actually being blocked. And this is what we're actually studying when we're looking at exoplanets as they transit in front of their star. So by how much light is actually blocked, we can know how big that planet is, but we can also study the atmosphere and what it's made of. And so the first planet that we actually looked at was a planet called WASP 96b. So this is an extremely big planet. It's bigger than Jupiter, but it's only about half the mass of Jupiter, which means it's got a huge puffy atmosphere. That atmosphere is full of what we believe to be hot water, which is what we actually were able to observe and as shown here in the James Webb Space Telescope spectrum. So what you're seeing is a series of hills and valleys as this planet passed in front of its star. We were able to determine that the composition of this planet's atmosphere was water. What was surprising about this first spectrum, though, is that the hills and valleys aren't as big as we thought they were going to be. And that means there's probably clouds or other things happening in this planet's atmosphere that we had no idea were happening before. So what we have to do is understand what that environment looks like. Is it something like Jupiter with great red spot and giant clouds sort of streaking across the sky? Or is it something a bit more transparent or maybe diffuse? Understanding what the composition of these planets' atmospheres look like is a really keen interest to us to understand if there's other planets that might have a composition that look like Earth's. Or maybe they look like Titan, or maybe they look like Jupiter. These are all extreme unknowns and sort of our quest with discoveries that are to come with the James Webb Space Telescope. Well, since this planet was observed, we also observed another planet within this that was close by. This is WASP 39b. And again, this is actually published science results. So this is our first spectrum that was actually obtained. And what we were able to do is we looked at this planet, and again, as it passed in front of its star, we watched how that starlight was actually blocked when the planet went in front of it. And then we looked with extreme detail at different wavelengths how much that light was actually blocked. And we were able to then determine that carbon dioxide actually existed in the atmosphere of this particular planet. Carbon dioxide is something that had never been observed in a planet outside of our solar system before. So this was considered a huge achievement for us with the James Webb Space Telescope, as well as for the science community studying planets around other stars. The other way we study exoplanets is by watching trying to study the planets directly themselves. So instead of them passing in front of the star, we try to image them directly. So the way we do that is if we point the telescope at the star, but then we put a giant lens in front of that starlight so that we can see anything that's fainter in the nearby vicinity, such as planets. And sometimes we even get lucky enough that we see planets with moons. We're not quite there yet with the James Webb Space Telescope, but we were able to image our first planet. And we did so around the star called HIP 65426. and the planet was actually B, the B planet of this particular system. And so what you're seeing is the different camera filters that we have with the James Webb Space Telescope on the bottom here, showing you different wavelengths of light that we've actually imaged this planet in. So by imaging at different wavelengths, we can also understand what the composition of that planet may or may not be. And then we can start to discern things like, you know, whether or not this planetary system has a puffy atmosphere, or this planet has an atmosphere, whether it's more terrestrial or a solid type of planet. These are the kinds of things we're really interested in studying. The funny shapes that you're seeing as far as within the images themselves just has to do with how the images were acquired with the different cameras and the filters that we have with the James Webb Space Telescope. I assure you they are all point sources, tiny little planets. And this is something that we're just starting to understand how these filters are working as we're doing these imaging. The star is showing you where the star would actually be in these images that we've blocked out with our technology. But we've also been studying things a lot closer to home, including the giant planet in our solar system, Jupiter. So Jupiter is something we can see with our own eyes, just walking out on a dark night, moonless night mostly. And you can see this big, beautiful planet with your own eyes. We have spacecraft currently orbiting Jupiter and taking absolutely amazing images in details that we aren't able to see with most telescopes. So what you're seeing here are some images that were actually taken with ground-based telescopes in the top left. These are at two different wavelengths. One is at visible light on the left. The reddish one is actually at infrared light, so something that we are studying with the James Webb Space Telescope. And then the large image is actually from the Juno mission, showing you the beautiful structure of the atmosphere of Jupiter and highlighting the great red spot. Well, we were able to look at Jupiter with the James Webb Space Telescope and study it in beautiful amounts of detail. Not only do we see all that fantastic structure in the atmosphere with the James Webb Space Telescope with our resolution, and surprisingly, with the extreme amount of sensitivity of JWST, Jupiter wasn't too bright to actually look at. In fact, we were able to see things that we haven't been able to study in a lot of detail, especially with remote telescopes or telescopes on Earth or those such as the Hubble Space Telescope before. What we're seeing now are rings that are being totally illuminated and lit up in ways that we can now see readily with the James Webb Space Telescope. The smaller moons that are harder to see with our naked eye, and even some of the aurora of this giant planet. The great red spot looks bright white in this image, and that's just because it's emitting at extreme temperatures that are quite hot and showing us the different amount of radiation coming from that particular storm. And the fun part about this image is all these little dots in the background. These are all actually photobombing galaxies in the background of this image, and something that we don't see very routinely with a lot of ground-based telescopes when we look at planets in our solar system, just because most of them are blocked from a lot of light that we can't see. And of course, you can blow this image up and use different filters of wavelength and understand all the different things and dynamics that are happening. But in the interest of time, I'm going to move on. Yesterday, we revealed Mars with the James Webb Space Telescope. Mars is actually the brightest thing, one of the brightest objects the James Webb Space Telescope will ever observe. It is the brightest infrared object in our night sky in our own solar system, and probably one of the brightest objects we will study, even in our own galaxy. So what you're seeing here are the two images on the right are the ones from the James Webb Space Telescope. They're at different wavelengths of light, and they're basically showing you the heat being mapped across the surface of Mars. And so we have sort of an image to show you what we're looking at within these two images. And one of the fun parts about this is we actually focus in on the Huygens crater. And what we're seeing in these heat maps is we can actually see that that crater has a different temperature within it. This is really amazing. And even the Hellas Basin also has a different temperature. This is because they're actually lower in altitude. So you can think as you go up a mountain, the altitude gets a lot higher, the air gets a lot thinner, and it also gets a lot colder. So as we go down towards the ocean, the air gets a lot thicker. And what we're seeing is that thicker amount of air causing this sort of heat to be perceived in these craters. So the crater up here on the top compared to the Hellas Basin here on the bottom, we can definitely start seeing some of these things. It is a really hard observation to do because it is so bright. We tend to saturate most of our wavelengths. And that was shown in the spectra that we have here. So when you're seeing the spectrum sort of cut off on the bottom, that means it's actually saturating with light. There's so much of that particular molecule at that wavelength that it's saturating our cameras, just like staring your own camera at the sun, for example, you would only see white light. But we were able to see some of the other molecules in the atmosphere of Mars, including water and carbon dioxide, as well as carbon monoxide. So with these type of spectra, what we can do is we can synthesize maps just the same way as we did with the thermal imaging or the heat maps. While we haven't done this quite yet with these data, we have run some simulations. So what you're seeing are some simulations of what we can and hope to do with the James Webb Space Telescope maps, showing you water maps and carbon dioxide maps that we hope to try to pull out of these data. And a comparison is what we have actually mapped from the ground. This is actually a methane map that was done with ground-based telescopes in 2009 at infrared wavelengths. So hopefully this is the type of science that's coming out of these observations, and stay tuned. Just looking forward, there's other things in our solar system that we will be glimpsing at. This is Uranus and Neptune, taken with the Hubble Space Telescope, and you're seeing these colored squares. This is what the James Webb Space Telescope cameras actually look like as we would see them across these two planets. The other images scattered around are different wavelengths of light, showing you what these planets look like at different wavelengths. We look at different wavelengths of light to study different parts of the planet. So what you're seeing here is all images across this entire figure of Uranus. And we're seeing it at visible lights, at mid-infrared light, at microwave radiation, and near-infrared radiation. And you can see they all look extremely different. And that's because we're basically looking at different depths of the atmosphere. So at shorter wavelengths, we're sort of limited to just right above the sort of what we would see as our own blue sky. But then as we go to longer and longer wavelengths, we start seeing sort of the outer atmosphere, and we can study that chemistry in a lot of detail. I'm going to go quickly through these last few slides. Interstellar objects are something that's very interesting for us, and we have all hands on deck for the next interstellar object to come into our solar system. So these are comets or asteroids that are actually from other planetary systems in our nearby galaxy that have actually been pushed out of their own planetary system and entered into ours. They don't stay, they come and go pretty quickly, but we're expecting to have our third one sometime in the very near future, and hopefully the James Webb Space Telescope will be able to observe it. Next week, we are sending a spacecraft to an asteroid system called the Didymos system. This is a binary asteroid, so it's an asteroid and its companion, and we're going to run a spacecraft into the side of the companion. When we do this, we're going to try to perturb or make the orbit of this second asteroid in the system slightly offset. And this is something we're trying to do just to understand if we can actually move an asteroid. So if you can imagine if one was coming towards Earth, we would want to try to move it so that it doesn't actually hit the Earth. And so this is what this whole mission is demonstrating. But it's also going to have some pretty cool science, and the James Webb Space Telescope will be observing this as we impact it to study the gas and the dust that come out of the asteroid as we run into it. So with that, I hope I've excited you with what we've already been seeing, and hopefully excited you about the science that we hope to be seeing in the very near future, and I can't wait to hear all of your questions. Thank you for your time.
Definitely, that is great. Just to reassure you right now, we've got some of our social media feeds have been quite interesting. There's certainly an interesting question about planetary collisions on Earth, which I'll come to later on. I don't think we're too terrified, but we'll go through that. We're going to get some time now for you guys watching this presentation to think about any particular questions you want to ask. And thank you for those who already posted it via the email link, via Q&A, by the messaging board as well. And we'll try and get to as many questions as we can do later on. But some people are really organised, and they actually did send in questions ahead of time to ask this based on the first episode that we saw in the Global Classroom. And the first one I'm going to read out right now, Stefanie, comes from Ratanakiri province in Cambodia. And the question is probably a straightforward one, which is, how do you decide on the different names of discoveries you come across, like Cartwheel Galaxy? Is there a Stefanie Galaxy out there that's about to be discovered as well?
So things like the Cartwheel Galaxy, that is its fun name. All of these objects that we observe across the galaxy, across the universe, all have sort of license plate type of names. These crazy HD 54328, whatever long numbers. And that's how we have actually assigned them and know where they are in the sky. Whenever there's an object of extreme interest that has a certain appearance, they will tend to get common names. We have planetary nebula with fun names. There's some called like the Cat's Eye Nebula or the Helix Nebula. The Cartwheel Galaxy is a beautiful example of something that it resembles a pinwheel or a cartwheel actually happening between these two galaxies that have collided. And so we do tend to give them sort of a more fun or common name, but its official name, if you were to actually have a reference or a citation of it, would be something a lot more dull.
So there's no Stefanie Galaxy around the corner about to be found?
No, but I do have an asteroid.
Okay.
So objects in our solar system can be named after their discoverers, or if it's an asteroid, somebody can name it on behalf of somebody else. And a couple of years ago, I was actually given an asteroid. And so there is an asteroid Milam out there, which is really exciting. That's
a great present, isn't it? On my list, past Christmas time, please can have an asteroid, just not the one that's being struck by NASA, hopefully, on that side of it. We've also got a question that came in from Nepal. We know the Nepalese people and the schools there really do watch Global Classroom and are very engaged. Let's try and transfer across and hear from Nepal their question.
Namaste, I am Salim Maharjan. I study in Analjati boarding school and I live in Nepal. My question, which image has been the most interesting or exciting one you have seen so far and why? Thank you.
That's an excellent question and a very hard one to answer. So the most interesting one for me is the Carina Nebula. So this is the giant cliffs of star formation that's actually happening in the galaxy. What I love about this image is, as I was trying to explain earlier, is we really don't understand what is going on. We are now seeing things that we've never been able to see or study about star formation, how that process actually works and actually moves from, you know, the very first stars starting to form in a cloud of gas and dust, how that nucleates or, you know, begins its whole process, and then how it moves into actual stars with planets around them. This is a whole new dynamic that we're really just starting to get some new insight into. And I'm really excited to see what kind of science is coming out of these types of images, along with the spectroscopy, which tells us not only about the composition of these objects as they're forming within these giant clouds, but it also tells us a lot about the dynamics. So how hot they get, whether or not they're energized. So we know as stars form, as they're collecting material, they have to somehow get rid of a lot of that energy. And so that comes out in what we see as like outflows. And so understanding how that energy is actually stored and carries through is very interesting.
Great answer, detailed one as well. Our next question is coming in from Sebastian, okay, who's really excited about watching you on the episodes here. Let's try and hear from Sebastian as well.
Hi, my name is Sebastian, and my question is, what is the most efficient method for spotting the Milky Way?
Okay, good question there. So I'm not going to suggest they use the James Webb Telescope, but what's the most efficient way of looking at the Milky Way from where he is?
So the most efficient way is probably on a night where there's a new moon, so there's no moon in the sky. You want to go out and when it's extremely dark, stay outside for, I don't know, an hour or so and stare at the sky and try to start counting stars. The longer you're out there, the more your eyes are going to adapt and you're going to see more and more stars. Hopefully there's no clouds in the sky. But when you're out there, yeah, you'll start seeing more and more. And if you're at a nice dark spot, so somewhere away from cities, think about like a nice forest where there's a clearing that you could possibly go to, maybe in the middle of the ocean. There's all types of places that you can go that are extremely dark, as long as you're away from the city. And usually you can see the Milky Way, and it is absolutely illuminated. It is extremely bright, and it streaks across the entire sky, and you can see all kinds of things within it. And that to me is the best way to see the Milky Way. And I remember my first time I got to see it with my own eyes. It was a very memorable moment for me. As far as with other telescopes, it's actually hard to observe the Milky Way because it's so big, because it's so bright. Using a telescope makes it very, very hard to actually observe it. So using your own two eyes or even binoculars is probably the best way to do it.
Great advice. I know from my point of view, somewhere in the countryside, no lights on, and if you get up at the right kind of time, it just pops out the sky and illuminates it. It's extraordinary to go and see. So good luck finding that. I can imagine you're out on a boat somewhere in the middle of the ocean, perhaps just doing that, but make sure you stay safe with your family, with the life jacket on as well. Now, what I want to say, there's a lot of questions coming in right now. I'm going to try and get through them. Some are more straightforward, some are not. Let's go with some quick fire questions, Stefanie. First of all, I've got some coming in for some 4-year-olds that are watching this, believe it or not, some very young children. And this could be a really quick answer. They simply say, what's a galaxy?
A galaxy is where stars and planets actually form. It's a whole collection of stars and planetary systems like our own solar system. So we exist within a galaxy that has hundreds of millions of other planetary systems within our own galaxy. And so that is what a galaxy is.
Brilliant. Great answer to that. Thank you very much for that reception class writing in there. And we have somebody called Harry, who I think is based in London. An interesting question was asked early on in your presentation. How can a nebula affect the atmosphere of galaxies close to it?
That's a really good question. It will affect the area mostly by the composition of that nebula. So as this gas and dust is being lost from the star, that cocoon of material, it actually keeps moving away from its central star that it came from out into the galaxy. And so what you're seeing is all of that gas and dust is now going to reform one of these giant clouds, just as we've imaged with the Carina Nebula. And that is where new stars are born. So what we're seeing is a whole recycling of material of stars. So as they're born, they are born out of these giant clouds of gas and dust. That turns into a new star. That star eventually dies and loses all of its gas and dust and forms a new cloud. So this is the cycle of stellar life that we're actually observing in real time. Wow,
fantastic. And a really good question that as well, I must say, coming in, is paying attention to your presentation. We've got an anonymous question, which I will address as well. I think my team are trying to publish these as fast as possible, which is, why is Mars so bright?
Mars is so bright because it's hot.
Good answer.
It doesn't have, well, it's so bright in infrared wavelengths because it's so hot. So Mars has a very diffuse atmosphere, which means that the atmosphere around Mars is very, very thin, and it's actually full of dust. We see actually large dust storms happening across the surface. But the composition of that atmosphere being mostly carbon dioxide and carbon monoxide, is very, very bright at infrared wavelengths. That's where the fingerprints of those molecules are actually found. And so when we look at it with our infrared eyes or our night vision goggles with the James Webb Space Telescope, we're seeing extreme amounts of carbon dioxide. And that's what makes it so bright. And it's also extremely hot because it doesn't have an atmosphere to keep it nice and cool and protected from the sun. So most of the heat and the radiation from the sun actually hits the surface of Mars, whereas our atmosphere here on Earth actually protects us from a lot of the radiation coming from the sun. So it's in a very extreme environment, and it's very, very warm there, especially when it's being lit by the sun, as well as the composition of the atmosphere. It's a great question.
Right. I've been told by my team behind the scenes, we will get the questions coming through the social media in 1 second. So thank you for those posting. I think someone like Jenna and Anna, who will be there shortly. So just hang on a second. I'll go as fast as I can. So Ethan wants to know, how long does it take to get the pictures?
Oh, that's a great question. We actually aren't very far. 1,000,000 miles away seems like a really far distance, but considering how fast light travels, we're sending back our signals at light speed, and it only takes a matter of moments to actually receive any of that data. That being said, we only send data a few times a day. So any image that is taken is mostly stored on a computer on the spacecraft, and then we send it down a couple of times a day. We sort of unload the computer of all of that memory, and so we can collect new images and data. But it's a matter of minutes, and it's usually within the scientist's hands within less than a day.
That's pretty impressive, isn't it? It's incredible. Now, Zara has probably, I think, a good question, actually. How many filters does a telescope have, and how are they deployed?
Oh, goodness. I don't know.
I think the answer is a lot. It's a lot, isn't it, in some ways?
Yeah, so we have a number of filters in each instrument. So we have 4 science instruments. The near infrared ones have a whole series of filters that actually, it's a lot more complicated. So we can combine them in ways that we can make the filter what we call extremely wide or extremely narrow. So if we want to study really bright objects like Mars, for example, we use a really, really narrow filter because we don't want a lot of light coming in at one time, or it saturates our cameras. So we have to sort of, think about putting your hand up and making your own telescope that blocks a lot of the light so that you can see something in finer detail. So that's sort of what we're doing with these filters, is we're trying to block all the other light that's around so that we can see something a lot more clearly. And if we're looking at something far, far away, we want to use a broader filter so that we can collect all the photons coming from that object, all the light, all the radiation, and that helps us study it in more detail if it's a lot fainter. So each one of our instruments has a whole series of filters, and then we have these wide modes and these narrow modes, and then we also have our spectrometers. It's a very complex machine, and if you're interested in the details, I'm happy to give you all the information on all the instruments, and you can imagine all the different ways we can put the pieces together.
That's really fantastic. I think that Thomas has posted quite a few questions on here to look at. We have Thomas coming in, who is, let's go with a question saying, do you believe space has an endpoint? Now, this is obviously a belief question, rather than, I don't know if it's how factually we can say that from that side of it, but how would you respond to that question?
So how finite is space? I don't think that there is an endpoint. The problem that we have is we know that, time is relative. And going back towards the Big Bang, as we're trying to do with the James Webb Space Telescope. So we want to study these sort of infant galaxies of the universe. But you can imagine as you go further and further back in time, you're getting shorter and shorter to what we would consider the Big Bang, which actually is not a climactic point and finite moment. You can say, I'm down to the last minute of time. I'm down to the last half minute of time. I'm down to the last second. I'm down to the last 0.00000000001 seconds. So you can imagine it only gets smaller and smaller, but that's just because it's relative. and it has this whole sort of infinite realm of how small in time you can actually get. So reaching that at a finite point is not something that I don't think exists. It was sort of some extreme moment, but we don't think it was an instantaneous moment. And so that's a really hard question, and a great one to pass by cosmologists for sure.
A great answer as well. I think you're doing really well for these questions. So there's 2 or 3 questions coming in, 2 on social media, 1 on the Q&A as well, that refer to about finding things to support life. One, Jenna talks about the idea, you know, what if you found something, what would happen? And Oliver mentions what would happen if you found an exoplanet that could, and I presume hypothetically, support life. And life in what extent, I presume?
Yeah, that's a great question. So as I've said before, we're not looking for life itself. We're looking for these sort of signatures in an atmosphere that would suggest that something is different happening in that planet. And the way we know something different is happening, something dynamic is happening with that planet, is by the composition. So we look at different molecules, and if certain molecules are there, others should not be there if there's nothing happening. So imagine how life influences our own atmosphere here on Earth. But there's other things that can change an atmosphere. Think of volcanoes, for example, or dust storms, or the giant red spot on Jupiter. That actually changes what we see in real time. So understanding what is actually happening is a real key question when we find something that's interesting. So say we do find something that looks, that has water, carbon dioxide, methane, carbon monoxide in the atmosphere, maybe even something like ozone or oxygen, then we start looking with other telescopes to understand that composition a little more in detail. So James Webb has a fantastic capability of studying these molecules, and we can do so in a nice timely cadence to understand if that's a dynamic system or not. So whether or not it's like a stagnant atmosphere that's just, you know, it has that composition and we don't know why, or if it's something that's actually happening in real time. So like volcanoes or impacts from comets or asteroids hitting that planet. But at other wavelengths of light, so if we go to longer wavelengths or shorter, we can understand that composition a little bit better. And so as we move into narrowing down planets of interest, that we're like, hey, that might be something that's really peculiar. Let's see what's really there. We'll look at it with more and more telescopes and do really detailed studies to understand why it's different. And hopefully that leads to something even more intriguing and more questions and probably more technology that needs to be developed. But it's definitely giving us that hint of something unique, and that's what we really want. And we are looking forward with the James Webb Space Telescope.
And that's incredibly exciting to hear, isn't it? That's what gets you sort of excited about what's coming down, what's happening, what can we see on a spectrometer. It's really exciting. We've got a question from Caleb, who's written down here, will the JWST help us land people on Mars? Interesting question. What do you think?
That's a great question. What we will be doing is understanding the composition of the atmosphere, as well as, you know, the surface features across the surface of Mars. And so how that contributes to future missions is really something of a nice speculative thing to provoke. When we go to Mars, we want to go somewhere interesting, but also that would be sustainable for supporting astronauts, for example, if that's where the goal is. If we're sending a mission for science, we want to go somewhere that's intriguing scientifically. So sending things to the crater, for example, because maybe there was water there, or maybe that crater was formed from an impact. Can we see what that impact was? Did it have an influence on the local, you know, environment? So you can imagine if something hits the surface of Mars, does it splatter across the surface, or does it just make all the dust and the gas of Mars, you know, plume up and go away? So I think depending on what you're talking about, as far as when we go to Mars, if it's a spacecraft for scientific missions, that definitely could be impacted by what we discover with the James Webb Space Telescope, or even not even discover, but maybe even just are able to characterize in a global scale. Orbiters and rovers are in very specific areas. So an orbiter, you can think of being on an airplane and you look out the window, you can see things like the ocean or a certain continent or sometimes even cities. You're only seeing the ground sort of right below you. Whereas if we're looking through a telescope, we see the whole globe. We see, the full surface of Mars. And so getting these different perspectives and putting all the pieces together definitely will influence where we do go, especially if it's a human-based astronaut mission or if it's something like a scientific mission. I think we will definitely be pushing on those locations. And
I like the idea from Caleb saying that, when we land on Mars, not if or just. He's obviously very, very positive on that side of it, that it's going to happen. 2 quick questions probably as well. Which one was that? Bella's written in as well to the message board saying, why do we use microwave radiation to view planets? Now, Bella might be thinking about her microwave at home. I don't know. She's got the kitchen, but see, you mentioned in your presentation about using microwaves to see what's going on. Why do we use those?
Absolutely, that's a great question. So different wavelengths of light actually give us different information about a planet or its atmosphere. So going to longer wavelengths actually gives us access to different molecules that we can now study. So we're looking at fingerprints of, let's say, more complicated chemistry or things that we can't access in the infrared. And when we go to shorter wavelengths, we're seeing other types of physical processes or chemistry. And so that is one reason why we would use a different wavelength, is to understand how that chemistry or that atmosphere is actually changing, or what the actual composition may or may not be. But the other reason we use different wavelengths is, as I was trying to highlight briefly, is we have access to different levels of the atmosphere. So sometimes clouds in our own atmosphere form really, really high up, and sometimes they form really, really low. And the composition, even how they look, are completely different. So really high up clouds are sort of feathery, whereas ones that are closer to Earth in the lower atmosphere tend to be more puffy and cotton ball looking. So understanding what the composition of our clouds close to Earth versus those in our upper atmosphere is something of extreme interest. Also, the chemistry that happens in the upper atmosphere, how that makes things rain down onto a surface. Do they have water rain like we have, or is it something totally different, like on Titan, where they have methane and ethane rain that rains down into the atmosphere and forms giant lakes of these carbon chemistry lakes? That's something we really want to understand, not only within our own solar system, but as we're studying planets around other stars. As I was saying earlier, putting the pieces together about what's causing that planet to look different. Why does it look peculiar? Why does it look like it has an atmosphere like Earth? That is something that we have to put all these pieces together and understand. Is that just chemistry happening at the very top of the atmosphere? Is that something that's actually being started or initiated by surfaces, geology on that planet's surface?
I've got also a question coming in about probably, I'm not too sure how old Jenna is. Okay, but hi Jenna, thanks for watching the episode. Jenna says, really enjoy what you're doing here. I've enjoyed both episodes. How can I do a job like yours? Now, I presume Jenna is speaking to you, not me. Okay, because that's probably a different kind of question. I won't answer about being in charge of schools, running schools, global classroom. So Jenna, I won't bore you with my educational background. I presume your question is for Stefanie. So Stefanie, how could Jenna do a job like yours?
That's a great question. And something I want to emphasize here is working for NASA, working for the European Space Agency, or any space agency across the world. We need scientists, we need engineers, but we also need people to help us do our job. We need computer programmers. We need people that can put together these fantastic videos and simulations. So even being a video game programmer is something or a person that could get a job at one of these agencies. So my background is actually in chemistry. I got a job, or I got my education in chemistry because I wanted to be an astronaut. And I figured as a chemist, I would be able to conduct experiments on the space station, or if I were to ever go to Mars, I would be able to do real-time science and chemistry there on the planet. And that I thought was a unique skill that would be very helpful for an astronaut. But also, it turns out I can do chemistry anywhere in the universe now. using telescopes and spectrometers and these imaging capabilities, we can study chemistry in ways that you don't necessarily get to do here on Earth. And that's really, really cool, is understanding the chemistry around the universe, in planets' atmospheres, in planets around other stars, or even new stars that are being formed. So what I will say is, how do you get to be, how do you get to work at NASA? How do you get to work on the James Webb Space Telescope? It's doing what you love doing. I loved being a chemist, and I loved my job as a chemist. And that has actually been what enabled me to get this job. I study chemistry in space, and that is why the James Webb Space Telescope chose me to work on this mission and to help them understand our own solar system and the chemistry in it with the James Webb Space Telescope. So do what you love and do it very, very well. If you want to be a scientist, science as much as you can science, math, computer programming, but also things like history are really essential. So being able to know what has been studied before you even studied it is a whole history lesson in and of itself. Every time we make a new discovery, we have to understand where that discovery came from, what is already known, and what we've learned. And so just do what you do very well and be passionate about it. If you're not happy with what you're doing, then you're not going to be happy with your job. So that is my one piece of advice.
Enjoy what you're doing, be passionate about it, find your passion, and be excited about it. We do have a question coming in. It's an anonymous one, so I can't say who it's from. It's referring to a Nancy Grace Roman Space Telescope, asking what does it perhaps look like in the future, and what are NASA's plans in the future, what are they aiming to achieve?
That's a great question. So the Nancy Grace Roman Space Telescope is the next thing that NASA will be launching as far as astrophysics telescopes go. So this will actually launch in a couple of years. So we're still a little ways away, but time seems to be flying, especially as I get older. So this telescope looks like the Hubble Space Telescope. It's in a can or a tube, the same way Hubble is, and it has an optical mirror just the same way the Hubble Space Telescope does. It operates at near infrared wavelengths, so sort of the very edge of where the James Webb Space Telescope and Hubble actually overlap as far as what light they can see. And instead of being an object or a telescope that's going to study individual objects like individual galaxies or planetary nebula or Mars or Jupiter, what it's going to be doing is it has this huge camera, and it's going to be mapping the entire sky with extreme sensitivity, because the technology that we have, in a field like a picture that's 100 times bigger than anything the Hubble Space Telescope can currently take at any given time. So we can do huge images across the sky with this telescope and really understand things that are happening, like whether or not a supernova is going off, how galaxies are merging together, whether or not a star dies. We'll be able to see new asteroids and comets that are flying across these giant camera images. So the discovery space that will be enabled with the Roman Space Telescope is something that's really exciting. And it really complements what's coming online from ground-based telescopes perspective. We have the Rubin Observatory, which has a large sky survey as well. So the Roman and the Rubin will work sort of in sync, very complementary to one another, and really help us with the discoveries of these new things that are happening across the galaxy, across the universe, that are hard to find if you're not looking.
There's some great plans for NASA going forward and to explore the stars further and push our boundaries and what we can learn and understand. Got a fun question coming in now from Kihan. I hope it's pronounced correctly. I think what you're trying to say, Kihan, it's quite tell on the texting side of it. Should I be worried about an asteroid colliding with Earth? Question mark, question mark, question mark. What do you think, Stefanie?
That's a great question. We actually have meteors and small asteroids hit Earth pretty routinely. The big ones are the ones that you need to be worried about. And the good news is we don't currently know of any big ones that are going to hit Earth yet. So
thanks for the reassurances there.
All of the major, the really large ones we know about. We've actually been able to study them in great detail. We know their orbits at a very precise level, and none of those orbits are going to collide with Earth. And so that's the good news. Those are the big ones that we know about. There are things that we don't know about, though. Interstellar objects are now a new thing. They're not the two that we've had. We've had two now that we know of. They haven't been very big. So chances are, if they even came near Earth, they would probably disintegrate and turn into basically what looks like a meteor shower. So just gas and dust sort of raining onto our atmosphere. Nothing really too extreme, maybe a boloid in the atmosphere. I don't know if you've seen these fantastic videos, like dashboard cameras of these things blowing up in the atmosphere. Those are usually rocks or space debris that are coming into the atmosphere, but they get so hot when they're coming in that they tend to disintegrate, or sometimes if they have a lot of energy, they will do these mini explosions in the atmosphere. They're really cool to see. They do happen actually fairly routinely. So big asteroids are the ones to worry about. We don't know of any that are coming towards the Earth. There's the things that we don't know about, which is why these big surveys are going to be critical. Things like the Rubin Observatory, the Roman Space Telescope, they'll be surveying the sky and looking for objects that are coming anywhere near us, as well as just understanding the objects that are there and being able to map them and understand what their orbit and their trajectory looks like. That way we can do full dynamics and studies and know whether or not there is a potential for them to be a hazardous object. But I can say today, there's nothing treacherous out there that's going to impact us.
So today we'll stay safe and not worry. And say today obviously is a good day and a positive day for sharing that. Can I say thank you to Mark, Anders, Karen as well, posting in there, who asked very similar questions and positive comments towards you, Stefanie, about the presentation we're doing so far. I know that time is starting to move towards an end. First, apologize, I can't read out all the questions that are coming in because I think it would take Stefanie so much time that she can't get back to analysing data coming down from the telescope as well. If I pause for 1 second and say, Stefanie, any message you want to put out to the children watching this today, or indeed their parents watching it, from yourself?
Absolutely. The one thing I want to say is the James Webb Space Telescope is the next generation space telescope. This is what students today will be using for their science tomorrow. I grew up in the era of the Hubble Space Telescope, and we fortunately still have a wonderful space telescope that we still use today. James Webb Space Telescope is going to be that next long-lived generation space telescope. We have what's predicted to be about a 20-year science mission lifetime now. So that means kids that are, or students that are, in grade school now, as you graduate from school and you move through university, maybe you get an advanced science degree, you too can use the James Webb Space Telescope for your own science, for your own discoveries, and it's something that's well within grasp. Anybody in the world can use this telescope, so hopefully this inspires you and makes you think about what kind of discoveries you would want to make with the James Webb Space Telescope.
That's brilliant. Thank you, Stefanie. And I think the overriding message there, this is your telescope, folks. It's amazing to go and see. We'll signpost you towards the NASA website. You can follow their Twitter feed, the social media feed. They post extraordinary images on there. You can go and see what's happening on their telescope. From all of us here at the Global Classroom, we want to share with you the exciting world around us, in our stars, in our skies, and our land as well. Tune back onto our website to view our previous episodes and our future ones coming up as well. From myself here, the Scaresbrick Hall, home of the Global Classroom, and for Stefanie as well. Thank you for tuning into our episode today, for exploring the stars too, and good luck, take care, and goodbye.
Thank you so much.